All right, let's do some parallel plate examples. I hope you all had a good weekend. We have got kind of just a different lesson today because we're just going to do 5 examples together. And then I want you to just, if you haven't already, I want you to try to finish those parallel plate examples that are in your homework booklet. And we will move on. I don't know, potentially see us moving on. I'll give you another day, but we'll move on soon. Anyways, let's get started. Our first question, they start off pretty straightforward. They get a little bit trickier. I do actually think that they're trickier in your actual homework, especially the last one, but that's always the same way, right? If you can't figure out how to do that last one, it's not the end of the world, especially since we're not in the classroom together where I could normally help you out. Those ones are meant to be a little bit more challenging. That's the whole point of that. So it takes 0.050 joules to move a 0.20 microcoulomb charge from point A to point B. What is the potential difference between these 2 points? So just to remind you, these are all these new terms that we learned in the last lesson, right? So if you haven't done this yet, you're going to have no clue what's going on in this question or in these questions. Make sure that you've done these notes already so that you have your formulas. Now, another good idea would be to have your formula sheet out right now so you know what formula to use. So let's write down everything that we know. So it takes 0.05 joules. Joules, right? That's a unit of energy. So it takes our electric potential energy, I'm going to use that one, is 0.05 joules. Okay? And then we're moving the charge, so our Q value is 0.2 times 10 to the negative 6. I kind of want that to just become second nature for you, just converting microcoulombs to coulombs. And we're trying to find potential difference. That is delta V, not velocity. So that's an uppercase V. So delta V is equal to the electric potential energy divided by potential difference. That's our formula that we use. So 0.050 divided by 0.20 times 10 to the negative 6. That should give us our potential difference. And if we do that, we should get 250,000. What do I measure potential difference in again? Volts. We can use volts, right? And just so you know, we can use volts or we can use joules per coulomb. Just joules per coulomb, right? This comes from energy divided by charge. So anyways, there's our final answer. Pretty straightforward so far. Let's move on. How much electric potential energy is lost when 25 coulombs of charge goes through a potential drop of 120 volts? So I'm going to use a different color just to write down the actual information that we have. Our charge is 25 coulombs. So Q is equal to 25 coulombs. We have a potential drop of 120 volts. So drop here is very important, specifying to us that we have a potential difference of negative 120 volts. So we're losing 120 volts of potential. And we're trying to find what the electric potential energy is. So formula, same as above, just rearranged. Now we're trying to find EE, right? So E is equal to Q times delta V. I just moved that Q over to the other side. So 25, and I wrote down, oh, that's right, 120, negative 120. So what this is going to do is just going to end up giving us a negative number, but all the negative number means, so if I do 25 times 120, that's 3,000. So negative 3,000 joules. That's our electric potential energy. This just means 3,000 joules, right? Like basically all this is saying is 3,000 joules energy lost. factorial. Okay, not actually factorial. An electron accelerates. I mean, I hope you guys are being able to follow it so far. We're just using that one formula, so this gets a little bit trickier. An electron accelerates from rest for potential difference of 250 volts. How much electric potential energy did it lose? And then you'll see this kind of often or semi-regularly where the question will ask you to specify your answer in both joules and electron volts. Okay, so you got to show me joules and then you got to do a conversion to electron volts at the end. So, accelerates from rest for a potential difference of 250. Oh, the key here, right? Okay, so this doesn't look like we have enough information initially, right? Because we have potential difference of 250 volts. But we've also been given another piece of information here. What's our charge? What does this question say? An electron. We know what an electron's charge is. It's either 1 EC or it's 1.6 times 10 to the negative 19 coulombs, right? And that's just the magnitude of its charge. It could be negative, right, because it's an electron, but we'll just leave it as positive. We'll leave it as the magnitude because we're only looking for, it's already saying how much potential energy to lose, right? So we don't need to get that double negative in there. Whatever we get, we just know that's how much energy it's losing. Yeah. I'm trying to decide if I want to put a negative in there. Honestly, you can if you want, but you really, really don't need to. So, let's get started. So we're trying to find what the electric potential energy is, right? How much electric potential energy did it lose? So EE, same one as the before, is equal to Q times delta V. So 1.6 times 10 to the negative 19 multiplied by 250. And that gives us an EE of 4.0 times 10 to the negative 17 joules. Okay? So 4.0 times 10 to the negative 17 joules. So there's our answer in joules. Found that one. I got to do this one, right? So how do I convert that? What do I have to do? What do you think? What are we remembering here? What needs to change? The big thing here is if I'm gonna go back, I'm gonna show you because I don't want to just be talking while you're staring at something that you've already seen before. 1 EV is equal to 1.6 times 10 to the negative 19 joules, right? And that really comes from the fact that one elementary charge is equal to 1.6 times 10 to the negative 19 coulombs, right? So really the difference here is between me actually deciding to write out 1.6 times 10 to the negative 19 or actually just using, right? You can also just use 1 EC. Now in this case, because I know that 1 joule is equal to, sorry, 1 electron volt is equal to 1.6 times 10 to the negative 19 joules, what that means is to do it in EV, right? I have to do my initial number that I had here, 4.0 times 10 to the negative 19 joules, and I divide by 1.6 times 10 to the negative 19, right? 1.6 times 10 to the negative 19. And what that will end up giving us, and sorry, I guess I'll write this. I should have done it like this. 1 EV equals that, and not equals. Man, I'm having a little bit of a brain fart here right now. Sorry. We do our conversion factor, right? That's the whole idea. You do 1 EV times this, right? And then your joules cancel, and you end up with, this is the funny part about this whole question, is you end up back with what you had initially, 250. Because all we did was multiply by 1.6 times 10 to the negative 19. So it either loses 4 times 10 to the negative 17 joules, or it loses, it's fine, I've actually made this backwards in my color scheme here, or it loses 250 electron volts. So you could say dot, dot, dot of energy lost. And it's always exciting. Okay, so let's do, we've got, part B. Oh, right, okay, because it accelerated from 0, right? So it accelerated from rest, and it ended up accelerating in this scenario, right? So this electron was going through like some parallel plates, right? Remember, we're in the parallel plate section. It's going from one parallel plate to another. It was going through some parallel plates, and it accelerated. So however much energy, however much electric potential energy it lost, think about it like dropping, like a ball off of a roof, right? You're losing gravitational potential energy, but you're gaining kinetic energy because you're starting to move faster. So the answer here is actually really straightforward. It's the exact same numbers as in the last question. It's either 250 electron volts, or it's 4.0 times 10 to the negative 17 joules. And these are the same numbers as in the last question, but the big difference here, and this is kind of why you have to be like a little bit more specific, is you got to let me know that it gained this energy in this case because it started moving faster. It was going initially 0 meters per second, and now it's going to be accelerating a lot faster. So this is of energy gained. Okay, 2 more questions. How many electrons must pass through a potential difference of 400 volts if they are to gain 3.2 times 10 to the negative 15 joules of energy? It's kind of a tricky one. So it starts off very straightforward. It starts off, I'm gonna do it like this. We already know what we have here, right? We have potential difference here. We have electric potential energy here, and we're trying to find what the charge is. Right? Now, the question, how do I know that, right? The question is trying to ask how many electrons must pass through if they're to gain that much electric potential energy. Well, what you're going to end up finding first is I initially want you to find how much charge is gained or lost, and then convert that to the number of electrons that represent that amount of charge. So I'll show you. If I'm going to calculate right now how many electrons were gained or lost. So we're gaining energy, right? So yeah, this is perfect. So let's break down what we got here. We have got electric potential energy. We gained 3.2 times 10 to the negative 15 joules. And we had a potential difference of 400. And remember, it can either be volts, right? It can be volts, or it can be joules per coulomb. And the reason I'm putting this here, let's actually just forget this one right now. Look at this. If my joules cancel and the way that this math works out, it comes up. We know that we are finding my charge in coulombs. So the total charge is 3.2 times 10 to the negative 15 divided by 400 coulombs. And that's 8 times 10 to the negative 18 coulombs of charge passing through there. Now, if I know that much charge was involved, now I can remember that one electron, right? One electron is equal to 1.6 times 10 to the negative 19 coulombs. So if I convert from coulombs and I want to end up with just number of electrons, I take 8 times 10 to the negative 18 and I divide it by 1.6 times 10 to the negative 19 coulombs to give me how many electrons there were there. And if you do 8 times 8 to the negative 18 and you divide by 1.6 times 10 to the negative 19, let me put this into my calculator right now. 8 times 10 to the negative 18 divided by 1.6 times 10 to the negative 19, I get exactly 50. So 50 electrons passed through in order for there to be an increase of 3.2 times 10 to the negative 15 joules. So some different steps that we're maybe not used to seeing. But as with all this stuff, practice, 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 right? So one more question. A charge of 10 coulombs is between parallel plates. What is the electric field if the work required to move the charge is 3 meters? Sorry, you're moving it 3 meters, and the work required is 16 joules. So what formula am I going to use now? Well, let's write out everything that we have here, and I think it will actually help to realize what formula we need to use. So we have a charge of 10 coulombs. And we have, we're trying to find electric field. What is E equal to? We know that the distance or the displacement that we're traveling is 3 meters. And we know that the work involved is 16 joules. So where have we seen all of these in the same place before? You can go to your formula sheets and you can look them all up. The formula that I'm thinking that comes to my mind is that work is equal to the charge multiplied by the electric field multiplied by delta D. And where did I get that formula from? We did that formula right here, right? Work is just the change in energy, right? Q E delta D. And we got it from combining these other two formulas here. So that's what we're going to use. And once we know that we need to use that formula, this question becomes very, very straightforward. Isolate, like solve this formula or rearrange it so that you're finding an electric field, and you'll get work is equal to the charge, or sorry, energy. Oh my goodness. Electric field is equal to the work divided by the charge multiplied by the displacement. Wow, that was like an ultimate mix up I had there. Sorry. There we go. Okay. And if I do that, so my work is 16 and my charge is 10. All these numbers are so nice and whole. And 3. And we get that the electric field is equal to, if I plug all this in, 16 divided by 30, 0.53. And what do I measure electric field in? See, this is what's tough about this unit, is it's hard to remember all these things. Newtons per coulomb. And being at home, I mean, just look it up, right? You're right there. You just take a look in your notes whenever you need to. All that information should be there if I've done, my part properly. So there you go. And what's the potential difference? So now we can go back to the same formula that we've been using for the entirety of basically all these questions, and that is that the potential difference is equal to the electric potential energy divided by the charge. Right? We've seen it mostly in this format, but now I'm just trying to find potential difference. Right? So it's the format that we saw in all the way on the first question. But now we have enough information, right? We have enough information to do that. We know that work, so that's like the key here, is that work is equal to the change in the energy, potential energy, right? So the potential energy, the electric potential energy is also 16 joules. So doing that, we get EE, which is 16, divided by the charge, which is just 10, and we get 1.6 joules per coulomb. Or if you want to, you can say 1.6. I like using volts. And that's the potential difference. Okay, that is a lot for today. So I hope that most of those made, some good sense and that you were able to follow along. Best of luck trying these practice problems. I think you have 7 of them. So yeah, good luck with those. Let me know if you have any questions, and we'll talk to you tomorrow. If my recording